Morning, everyone. So, yeah, I'm Phil Towle. I'm the Rolls-Royce account manager. I've been with 3D Scanners about 10 years, and Carl's done a really good introduction as to what I've been doing most of that 10 years. I'm an ex-Rolls-Royce turbine designer who had an interest in metrology. I'm not a metrologist per se, but I maybe see things from a different direction to the way the metrologists do. So if you're interested in talking about what we can do for aerospace, especially aerofoils, that was my sort of design experience. Or if you want to have a chat about data loop, come and see me anytime during the day. There's one big thank you to go out to Ben Williams for the support that he gave us doing the data loop installation. So yeah, we've got an in-house guy, Ben, who does all of our data loop stuff. So he's been great with working with Rolls-Royce to get this data loop in earlier this year. So I'm going to cover some of the things that are new in PolyWorks 2025. Some of the things have actually come in the later versions of 2024, but a lot of you might have missed them. So some of them are brand new in 25, some of them in the later versions of 24. So the things I'm going to cover are the pre-alignment for laser scanning. I'm going to cover derived dimensions. I'm going to talk a little bit about the way we can now accept CAD assemblies in 2025, which is something else that I'm going to be working with Carl going forward. So the first topic is the scanning pre-alignment. So what's the issue? Why do we need a new type of pre-alignment? So we need to align the device to the CAD or a reference to make sure that all of our guidance benefits are available to us. I'll cover this in a bit of a demo to show exactly what I mean by the guidance benefits. If we're using surface point probing, that only works if you've got a probe available, and in a lot of cases you're going to need a special fixture to do that, to maybe clamp the part down to be able to do that initial alignment. The current best fit data to reference that we have requires nearly all of the data before it can actually do that alignment, which means that you can't do your scanning guidance because by the time you've got all your data it's too late, and that's the point at which the alignment gets done. And then if we're wanting to go into multi-piece inspection, then we need that robust alignment so that when we bring in the new piece, we can do that same alignment and get exactly the same every time. So what's the solution? We've now brought in a scanning pre-alignment. There's a little caveat on this. It only works for line scanners, and that's only single line scanners. But this is the solution that we've got. So essentially, we give you this scanning guidance. You basically say, where am I going to take my first line of data? What direction am I going to move my scanning line from there? And then the bottom view is just showing, as we start to do that scanning, the first scan that we do, it starts doing the scanning pre-alignment. As we take further passes over the scan, it then iterates that process, gets us nearer and nearer. After the first one or two scans, we can then do the scanning guidance. When we actually finish the scan and finalise it, we go back to the tree view, we've got the scanning pre-alignment, and we've got the standard best fit to reference that you are used to seeing. So, what are the benefits of this for you as users? Uninterrupted scanning workflow, no need to use a probe now. Feature scanning guidance for all, yeah, other than the fact that it's only a single laser scan. Also, I'll mention it at the end, but that scanning guidance isn't on a standard, so I'll show you that as we go through the demo. Increased repeatability for multi-piece inspection, as mentioned in the first slide. And then there's some other things, so negated risk of damage of probe when scanning. Quite often, especially if you've got extended probes on and things, it's quite easy to knock the part as you go past with the probe. No risk of moving the part, damaging the parts or deformation to it from the probe. So if we've got a finished part that's been painted or polished, we don't necessarily want to touch that with a physical probe. And then finally, we might not need to clamp certain parts as we don't need to physically touch the part. So your fixtures might just be a simple place it on the part rather than having to clamp it down because we're not actually physically touching that part with the probe. So I've got a quick demo. Just finish. Quite sure why that won't come to me at PolyWorks. Yeah, I'll just just close the...
Which one's yours?
Cheers on. So, I'm in the Workspace Manager. I'm just going to mention one thing while I'm in here. There's a little yellow band at the top. Because this project's got an IM-Align project in, it's just saying that PolyWorks 2025 is the last major release to include the IM-Align module. So we're losing IM-Align and IM-Merge in 2026. So if there's anybody who's currently using a workflow that uses IM-Align or IM-Merge, give us a shout and we'll show you how to do that within the other modules. So this is the part that we're going to take a look at. Apologies, let me just bin that. I must have saved this with it in. So essentially we've got a sheet metal part. It's got a number of features in there, so there's a number of circles, there's a number of planes, there's a number of dimensions created from the planes, and we've got a surface. So normally what we do with this part is we go in and we do a surface point pre-alignment. That would then allow us to scan and get our scanning guidance. So if I go to my device, what I'm going to do is I'm going to use the PolyWorks line scan player. So for those of you who haven't used this, the line scan player plays back a previously taken scan in the way the operator took that. So we can use this as a training aid so you can show people how you want to scan a part. Or what we can do is we can play back the scan in the way the inspector took that to see whether they've done that in the way we expected. So that's what I'm going to use as my device. Going to connect to that device, and then I'm going to select a scan file. I've got a scan file on this machine. I can't believe that. I'll come back to this one in a minute. Yeah, I'll tell you what I'll do. I'll use the offline simulation. I haven't got any plugins on either. Sorry about this. Yeah, so I'm going to connect to the devices if I'm connected to the arm, and I'm going to go and I'm going to start the scanning. So this pre-alignment works if I'm doing a surface scan or whether I'm doing a surface and boundary scan. This is the new button I've got here. I've got this pre-align during scanning. So if I tick that on, I then go to this defined scanning pre-alignment guide. I need to pick a point for where I want my first scan line to start, and then I need to give the direction in which I'm going to scan from that point. Yeah, when I'm ready to scan, I can just hit the start scan. And when it's taken the first alignment, it will then go through and it will do its first alignment. It'll keep iterating that. And then when it's finished, it will give us a best fit alignment. So wait for that to finish and I'll just show you what that looks like in the tree view. Yep, so in the tree view we've now got that new scanning pre-alignment and we've got the standard best fit to reference that we had previously. I'm just going to mention one extra thing while I'm in here. The select objects is now on as default. Yep, so just be a little bit careful with that. It used to be off as default. One of the other things that we've added in 2025 is we can now increase the size of the caption here in the 3D scene. If you're creating reports or you're looking at these things on your tablet or whatever, sometimes the text sizes are a little bit small. So we can now increase the size of the caption here in the top left. So under the edit annotation above that, or if we go through the menus to the formatting here, we can increase that 3D scene caption to make that easier to view if we're doing that on a tablet or we are creating reports that have got smaller views. Yep, so that's our new scanning pre-alignment. So let's skip on the next slide. Yep, so this is what we can see in the tree view. We've got the initial alignment. As it goes through, it will then pre-align to align those scans till we get our best fit as we've always had. So how do we apply that? We've seen the little tick box when we're connected to the arm. It's slightly different with the laser on the CMM, but again, we've got a similar tick box to apply that when we're using the laser on the CMM. So there's some best practice to this. The laser line should be in the same orientation and position as the starting rectangle. And then we need to move away in the direction of the arrow. So we don't need to start on an angle and then come off at a different angle. We need to follow that line. Yeah, the size of the rectangle doesn't matter. The length of the arrow doesn't matter. It's all about the direction of the line and the direction we're moving that line away. So the scanning guidance is off by default. We can turn that on in the little bar that comes in the bottom of the 3D scene. And then what we need to do is we need to place that scanning guide where we've got some features. So in this case, we've picked the cutout and the holes there so that when we do that first scan, we're actually picking up some geometry that's going to allow that pre-alignment to happen. If you haven't got that sort of geometry, you might be able to scan part of the fixture. If that doesn't fully work, you can maybe add something to your fixture to allow this pre-alignment to happen. Yeah, everybody happy with that? Any questions? No, you can come and see me later anyway. The second topic is derived dimensions. So the context of this, quite often in the past, we've seen people use positional tolerance on features. And when these features have failed, they've done a little bit of investigation to say, well, how far out is that feature and where is that feature compared to where I expect it to be? And they look at the X and Y positions of the center point of that feature. And I know there's two guys in the audience who do exactly this. And they take those dimensions, they put them into another piece of software, normally Excel, and they come up with a value of that position. Now, quite often they're not just looking at the value, they're looking at what direction it's gone in. So when we do the positional tolerance, that just gives us the value. It takes away the direction information. But when they do the maths, they get a different value to what the software gives for the positional tolerance. So what's the solution? We've now added in derived dimensions that belong to that positional tolerance. So we can give the X, Y and the Z position of a point reducible feature. And we can do this on the point reducible features, so circles, slots, etc. We can do the same for actual features, so we can do this for cylinders. And we can do the same for surface profiles. So I've got a quick demo. So you've got the same part that we've seen in the presentation. There's the circle that we were looking at. So we've got the positional tolerance, we've got the X and Y error of the feature. If we go into the geometry controls, we can either double click on the positional tolerance or right click and go into edit controls. And in there we can add in our derived dimensions. So in this case I'd be interested in the X and the Y errors. Yep. Now, previously what we might have done is we might have also added in the mating diameter for that. So we can go in and create the mating diameter, or we can do the X, Y and Z for the mating diameter. And this is exactly the situation we see. The centre X, Y and Z, the derived dimensions and the X and Y don't match. Now, we can make these things match. One of the reasons is we're not in the correct coordinate system. So the derived dimensions are always in the datum reference frame alignment. So we need to activate the datum reference frame alignment. And then in the case of the circle, anything that uses the datums is automatically setting the fit type on that. So to make everything match, we'd have to go into the properties of that circle. And we'd have to set the fit type to min fit. And then what we see now, we see that all of the values for the X and Y match up. So we could get these dimensions before, but it's now something that we can get automatically. And we can set these to come on automatically from the import of the CAD. So under the options, objects, controls, in there we can actually add that in as a standard value in our annotations. Similar for the cylinder. If we go into the cylinder, we can add in the X, Y and Z positions top and bottom, and we can also add the max deviation. What we'll find there is we'll find that the max deviation in the case of ASME matches either the top or the bottom values. In this case, it's the bottom values. If we go and change our GD&T standard to ISO, if you're working in ISO, the way it calculates the derived feature axis is different. So in that case, you'll only need to look at the maxes because it will never match your top or bottom. Yeah, and then finally for the surface, we can go in there and we can add probably the min and max deviations are the most useful ones for a surface. Yep, so that's our derived dimensions. So, in the failed scenario, what we'll be able to do. So, if they are pilot holes, we could re-drill before we put the holes in. And then, again, this is the example that the two guys in the audience will know about. Errors might be acceptable in a certain direction. So, the customer I'm talking about had floating fasteners, and if they all moved in the same direction, it could be acceptable. And then you had to watch they weren't coming too close to the edge of the part. So, movements in a particular direction might be acceptable, which you wouldn't be able to tell directly from the GD&T for positional tolerance. So I put a quick quote in here. What is not defined cannot be measured. What is not measured cannot be improved. What is not improved is always degraded. So this is a quote from Lord Kelvin. It fits in nicely with Adam's digital thread, but from a long way back. One of his better days, he also said that heavier than air flight was impossible, but we can all have a bad day, can't we? So with this, what I'm saying is that the intention of this is partly to make sure that when something fails, we know what's happened. But we can also use this when we've got a past scenario. So in the situation here, if we chart the position using the derived dimensions, so we could do this using Excel and the report loop plugin for inspector or data loop. If we chart where those locations are, if we actually looked at the SPC from the positional tolerance GD&T, other than the one that's right in the middle of that red bullseye, we'd actually get a very similar value. Because once we take out the directional information and we only look at the resultant value, the SPC is not really telling us much. If we actually chart the direction they've gone in, the one to the right, what we might be able to do is maybe amend the fixture to centralise that process. We might be able to amend the machining process to bring that value back in. Now, the one on the left, at first glance, that just looks random. So in the way we've charted that, it looks like maybe that's a random process. But if we then took that data and we charted that against maybe time or temperature, operator or gauge, we might suddenly start to see that there's something else affecting those values. So yes, it can be great for seeing what's happened if something's failed. It can also be useful if something's passed and we want to improve that process. Any questions on the derived dimensions? No? So my final topic is CAD assemblies. So most people will be familiar with CAD assemblies. This one's actually a CATIA one, so we've got an example of a radio controlled car. So people have used them in CAD for a long time. They allow us to better comprehend complex systems. So I'm just going through the terminology for the CAD just so that I can show you what this now looks like when we bring that into Inspector. So we've quite often got a top level assembly, in this case the suspension. We've got a first level sub-assembly, which in this case is the shock absorber. We've got some sub-assemblies at a second level under that, so in this case we've sort of got the damper rod of that. And then under that we've got individual parts. And then what we've also got going on is we've got some parts may have multiple instances within that. So in this case it's pointing out the two bolts at the top. Previously in Inspector, we haven't really been able to deal with this. So we don't tend to have any hierarchy in the earlier versions. It's a flat list of parts in a single object group. Far too much information to see in one go in the tree view. There's no sub-assemblies, and then we lose the assembly names, so we can't identify what belongs to those sub-assemblies. We can't deal with instances, so every time we use a part that's used more than once, we're adding time and memory to be able to show that within the 3D scene. So we've now got a new structure inside Inspector that looks more similar to what you see within the CAD package. So we've got the top level CAD assembly. That will then show us underneath how many instances we've got under that. It can show the sub-assemblies under that and the sub-assemblies that we've got sat under there. Yeah, we're taking the same hierarchy as you see in the CAD software. We've got the same naming convention, so we can search that in the same way we can the tree view in the CAD package. And there's no limit to the number of assembly levels that we can have under there. With the assemblies, most of the operations that you can use on your standard references work. So we can hide and show. We can delete components from that if we use the contextual reference tab. So we can use any of the operations that we had under the levels that we had for references previously. What we can't do is insert or add extra components. We can't group or transform components independently. The assemblies are a rigid block. When we're using CAD instances are shown by these light blue highlights, so we can see where we've got CAD instances, and they share the same surfaces, curves and triangles. And again, the assembly instances will share the same parts. So what do we get from that? So removing the duplicate geometry improves performance. In the case of this suspension assembly, It's a 17% faster import and 33% less memory use. In the case of this jet engineer, 41% faster import, 33% less memory. Now, this wouldn't be the case in every assembly situation. If most of your instances are small components like fasteners and things, then you wouldn't see these sorts of improvements. But yeah, where we've got sub-assemblies and lots of parts being reused that are larger, these are the sort of savings that we can get. Yeah, and that's it. So, any questions? Thank you.